you for the invite to speak on this on World Osteoporosis Day. I'm going to not say too much about osteoporosis itself or its treatment, but try and intrigue you into understanding how fascinating your skeleton might be. And on this introductory slide, I have a family photograph. This is my daughter, and this is a 3-day-old baby she produced. This is her mother-in-law, and this is her grandmother-in-law. So we have several generations that have different demands on their skeletons. Their skeletons experience different events, and by understanding those, maybe we can enable the older people to have a more active and higher quality independent living in their old age. The middle section I'll talk about more. This is normal spongy or cancellous bone. This is what's inside some of your bones in an adult, and this is what happens as you get older. It doesn't take a rocket scientist to see it's disappearing. I always carry a camera around with me, and I noticed this sign on a street corner, and it tells you two things. One, as you get old, you look like a banana. Secondly, women and men suffer from this condition. So we are getting gender equality, which UCL would like. And thirdly, it's often a one-way trip to the cemetery. So I'm trying to now give you some information on how we can perhaps exercise and condition our bones. And at the end of the talk, I hope to persuade you that it's nothing to do with bone, it's about your nerves and muscles. That may be a bit controversial. So this is the outline, a bit about osteoporosis, a bit about the skeleton, then a little about genetics. And if you look round, they're all different shapes and sizes, and I'll talk a bit about that, and then how we might think in terms of integrating that to optimize our bone strength. So you may have heard on the news osteoporosis is a huge problem. The only people that don't recognize it are the funding agencies. And this is what tends to happen as you get older. You become reduced in height, you get curvatures as your spine collapses, you become frail, you tend to fall, you don't have the right same balance, and when you fall, because your bones are not getting the input of youth, they are fragile and they break. Alan Boyd, who was at UCL, produces these rather nice scanning EM pictures, again, to show you in the trabecular network, which is inside bones, you'll see, come and have a look inside a bone, disappears, and that reduces strength. So on this slide, we see the amount of mass of your skeleton, bone mass, as a function of your age, and the two times when you may fracture are early on, when you're trying to learn to walk and stand. And actually, the reason I used the title was, at this stage, babies bounce, and children have green stick fractures. They don't break completely. And we'll come on to why that is later on. And then in your adolescence, you begin to put on bone as you exercise and you grow. And the only fracture risk there is usually sponsored by motorcycle companies. And then through life, you reach a certain level. And then at a point in your older stage of life, for women, particularly at the menopause, when estrogen levels drop, there's a dramatic loss in bone mass, women more so than men. And you enter an area where the bones are then at risk of fracture with normal everyday loads. So one theory is if we could increase our bone mass as we grow, then as we decline, we will decline, but we won't reach a fracture state until after we die, well, perhaps. So if you take a CT scan of a normal person, these upper pictures show the bones in the lower limb. This is the tibia down here, and the fibula. This is in the middle of the bone, and these are at the extremities of the tibia and the extremities of the radius down near the wrist. And if you look at these in an osteoporotic person, you'll see throughout the upper limb and the lower limb a thinning of the cortex, a loss of the internal bone structure, and a slight widening of the tube of the bone. So those are the sort of things we'll be looking at. And the more astute of you will notice that the cross-section of the whole muscle, skin, fat compartment is reduced, and the muscle is reduced. And those that are getting old will notice they're not as strong or as muscular as they were when they were young. So when you fall, you fracture certain parts of your skeleton. But without falling, you can actually get fracture of the vertebrae. These are the little bones that form your spine, which are nice chunky wedges in this, or sorry, chunky sort of cubes in this specimen. And they tend to break at the front. So that front collapses and makes a wedge. And this is what gives rise to the dowager's hump in osteoporotic patients. And that tends to happen with everyday activity. If you fall, then the common sites for injury are your wrist, as you put your hands out, or your hip. And hip fractures are actually very important. And we want to understand why this happens, both in terms of the bone quality and in terms of the neuromuscular control of falling. Why is this? Well, falls are key. Hip fractures are devastating. If any of you know old people that have fractured a hip, they usually lead to hospitalization, complications, comorbidities, and probably 30% morbidity in the first year. Probably 30% people never go back to independent living and become institutionalized. And only about 30% actually get back to where they were, only to be told they now have a high risk of a second fragility fracture. And often, this is the only time they are diagnosed as being osteoporotic. So an awareness of your skeleton through life is actually important. And the cost to the health service is already phenomenal, and with the aging population, will become much more so. So that's the political bit. The healthcare service has to take account of this, and it will be as big, if not bigger, than strokes and heart attacks and other things that are well funded. I don't know if there's any funding people here. So the International Osteoporosis Foundation produce on their website a very nice little document to tell you in simple terms how you can take action to make your bones unbreakable. And the key factors in the diet are vitamin D and calcium and exercise. Vitamin D is perhaps an underrated vitamin. I'm told that everyone who lives north of Manchester is deficient in vitamin D. A lot of other countries are deficient, and a lot of other people in the south are actually deficient. So it makes you wonder whether the normal values are correct. Calcium is important, as you'll see, in building bones, and exercise is the thing I'm going to focus on because this is actually key to structuring your bone and maintaining its mass. So we'll come back to their recommendations later. So now let's look at the skeleton as a structure and as bone as a material. I used to be in Bristol, and this little slide shows the need to understand the relationship between materials and the function of the structures they use to build, from Brunel's suspension bridge at the bottom to Concorde, the supersonic jet at the top. And both those use materials in an appropriate way. The bridge in particular, the columns are stone, resisting compression, and the suspension is steel, resisting tension. One is like a rope, and one is like a mineral. So when we look at the skeleton, a lot of people perceive the skeleton as dead, inert, dry bones because you see them in museums. We tend to see them covered in blood and steaming in an operating theatre. But each bone is different. And that's because it has a different function. And that's bone as a structure. I'm going to dip down into it and look at bone as a tissue, because bone is the word we use for both. So individual bones with specific features are optimally designed. So what is bone? Well, we can look at it at a gross level, and you can come afterwards and look at these. This is a tubular bone with struts in the end. Why is it tubular? Most of your long bones are tubular, and that's because they are designed to resist predominantly bending and torsion. So if I take a floppy material and I roll it into a tube, then I get something that has resistance to bending and twisting. And if I put the material further out from the axis of that bend, it becomes stiffer, more resistant to bending. And if you look at bird bones, where they can't take excess baggage, they have very thin, very wide bones. So they've taken this adaptation to its extreme. If you do take it to extreme, it becomes like the aluminium beer can, and if you lean on it, it buckles. So in birds, they've put little struts in to stop the buckling. So that's fine for the middle of the bone shaft, where you're getting bending across the bone. So muscles running from one end to the other will allow this bone to bend or twist. And that is the best way to use the least possible material, so you don't carry excess baggage, and put it in the strongest format. At the ends, where the joints are, bones are loaded more in compression, and we want to reduce the force per unit area so we don't damage the joints. And to do that, we put struts of bone in. And if you look at this, this is what we call cancellous or spongy bone. And I'll show you in a minute in the slides, it's not randomly distributed. And why is that? So who looks strong here? Would you like to break that pencil for me? UCL can, spare no expense, right? Now, you bent it, and it's a solid strut. I want you to break that one, but I want you to break that one in a different way. I want you to break that one in either pure tension, pulling it, or pure compression, pushing it. So you can't do that. So if we put struts, very thin slithers of bone, in an area where biologically there is predominantly pure tension or pure compression, we can use very small pieces and very low mass. And nature discovered that before the Department of Engineering. So bones then are arranged grossly like this. And if we now dip down into the actual material, we'll see it's formed of layers. It's almost a fractal type arrangement. And these contain blood vessels and cells. And we'll come back to the cells. The material itself is a composite. It's collagen fibers, which give it strength, and mineral hydroxyapatite crystals, rather like chalk. Not quite the same as chalk, but mineral crystals, which give it stiffness. And it's that interaction that I want to focus on a little bit. There are 3 cell populations. This top panel here shows you a cross-section of bone looking down at the end. And these are the little arrangements of layers of lamellae in structures called osteomes, or in the old days, Haversian systems. And the little black dots contain cells, these yellow cells called osteocytes, which sense what's going on in the bone and send signals to these cells called osteoblasts, which form bone. And these cells then signal other multinucleate cells, like this one, that sit like little hovercrafts and secrete acid and eat bone away. So as we sit here, our skeleton is turning over. Osteoclasts are removing it, osteoblasts are filling it in, and osteocytes are telling them what to do. And the osteoblasts are making new bone. And new bone is this composite. If we take this bone, this is fairly strong. It won't break. If I'd actually been allowed to, we could have put a blow lamp on it and burnt it. But if we look at this video, this is a piece of chopped bone from a barbecue that has been heated. And as it's given a slight bending moment, it is fragile, it's brittle, it breaks. This is Professor John Curry in New York taking another bone that's been put in a mild acid, which has dissolved out the mineral and leaves the collagen. So it's like a tendon, it's like a piece of rope. So if we take the tendon, we add the mineral, add these two together, we get a strong composite. So it's easy to understand that the ratio of mineral to collagen determines the material property of that bone. How do we look at our own bone to see whether we can understand how strong it is, knowing those 2 factors? Well, all of these ways that we image bone tend to tell us the density of the mineral. So they'll tell us about the stiffness, not the same as the strength, as I'll show you in a minute. We've started looking at bone with a new technique, Raman spectroscopy, and I'll say a bit more about that because that will enable us to look at both phases. So the traditional X-ray or the DEXA scans, if you go and see how competent your skeleton is in terms of osteoporosis, only really look at mineral density. The collagen is invisible. And this is what is kind of intriguing. In the literature, we can plot the strength of bone against the mineral density, and we get a relationship. So it does tell you something about the strength, but only about 60 or 70% of bone strength can be explained from measuring the stiffness. John Curry, again, in York, took a piece of bone, and here he measured its Young's modulus, which is equivalent to the stiffness, and then he zapped it with radiation. And radiation damages collagen. So if we zap it with a lot of radiation, and then we measure its stiffness, or density, it's still the same. If we measure its bending strength, it's weakened because we've damaged the collagen. But you can't see those on X-rays. If we look at its work to failure, its toughness, we've dramatically reduced that. And toughness is important. That's probably why babies don't fracture their bones unless they have a genetic defect of osteogenesis imperfecta. So collagen defines the strength. So we need to understand both of these to understand the skeleton. And apologies to the experts. This is a slide lent to me by Professor Tony Parker to explain Raman spectroscopy, which essentially is firing a laser into a material, imparting energy causing molecular bonds to vibrate, stretch, or move around, changing the energy and looking at the color changes in the light from that change in energy and plotting it out on a very special spectrograph. And we get peaks, which I'll show you in a moment. So this slide actually tells you that we can look at the strength of your pint. But what it can do is to give us this array of peaks. And in the sort of yellowish and the red, I've separated out the peaks that relate to the collagen, and the peaks here, the phosphate and the carbonate peaks, which relate to the mineral. So this modality can tell us about the two bits that are critical in understanding material properties of bone. And with some collaborators, we obtained samples of bones from these mutant mice. And this mouse is a mutant mouse that resembles osteogenesis imperfecta. So this is a condition that babies have, and some parents suffer badly because they're thought to be maltreating their babies because their babies have fractures. And actually, it's because the bones are so weak, they almost break when they're touched. And they've engineered that gene into these mice. So we took the spectra with this rather complicated Raman system. And this is the little packet of Raman photons. There are very few of them. And this is a massive band of fluorescence that comes out when you hit the bone with a laser. And these optics separate this out, and we can look at these spectra. And then we did that in collaboration with Rutherford Appleton Laboratories near Oxford. And if we subtract the spectra from the normal mouse and the genetically mutant mouse, we get differences which tell us something about the chemistry of the collagen and the mineral affected by that genetic defect. So we can begin to tease out what it is that perturbs the quality of bone as a composite. That was a very expensive laser system that we bid for funds to use at Rutherford, and to make that practical, we have to translate it into a commercial tool that can be used clinically. It's low cost, minimally invasive, safe, and the other things on this slide. And we've done that. I can't show you this, so it's lucky I put a slide in. UCL didn't give us a laser. But this is a red laser light projector that you use for looking at screens. It's shone through the thumb, and it's red light, and it penetrates the tissues. So we can fire this in, and with a scientist at Rutherford Appleton, Pavel Matusek, who came up with the concept of offset Raman spectroscopy, where you fire a laser in here, the photons disperse in the depths of the tissue, and the further away you go from this point to collect your Raman photons, the deeper is the origin of those photons. What does that mean? That means that by using this offset technique, we can apply a laser to the skin and get information from structures like bone and tendon beneath the skin. So it becomes closer to being usable. And these very primitive early spectra again show collagen peaks here and mineral peaks here. So Kevin Buckley, who's just finished his PhD, working with some samples from John Curry, started to see whether we could ascertain interactions between mineral and collagen in bones that had evolved over time for different purposes. This is the tympanic bulla of a whale. It's the ear bone. It's very brittle, very dense, because it has to transmit sound. This is the leg bone of a sheep, which is in the middle. And this is antler of red deer fighting for dominance over the females. And if they were to be brittle and shatter, they wouldn't succeed. So these are tough. And if you look at the scanning EM on a fracture surface, the antler has got collagen fibers predominating, the tympanic bulla has got predominantly mineral. So we want to know what controls that, because then we might be able to control the ratios that cause osteoporosis. So we compared the spectra of these three, and you can see the peaks are slightly different for the three types of tissue. And we found that by ratioing the collagen to mineral peaks, we could predict the stiffness of the material. And we've done that in bizarre bones from a whole range of species. And then we found characteristics in this amide 1 peak, which is part of the collagen molecule, that seem to relate to the level of mineralization. So this is the first sign of beginning to get a clue as to what might be happening in some aspect of collagen that controls the amount of mineral and therefore controls the stiffness of the material, which may affect the structure. But that could have been because it was a whale, a sheep, and a deer. So then we went on to look at these three evolved bones in a single species. So we took a single deer, and we took the leg bone, the ear bone, and the antler, and again we saw the difference, and in the amide 1 peak, the character of these molecules. And that's an area we're actively progressing. This is sort of cutting-edge research. Then we looked along the length of a bone. Why did we do that? Because if you're a baby and you have low stiffness, as you get up on your 2 feet and start walking, you don't want your bones bending all over the place because it's energetically costly. So we want them to stiffen in the middle. And actually, using Raman spectroscopy and CT scanning, we can see in the middle of a bone there is a high mineral content, and at the ends of the bone, the material, not the structure, the material, has got a lower mineralization and is less stiff, so it would allow shock absorption. So again, confirmation of how wonderful nature is in adapting your bone to its functional requirements. This is my 6-month-old grandson. Maybe I shouldn't say that. And this is one of my research team. And this is the collagen. So niamide 1, a small difference. In the phosphate, which is the mineral peak, in the baby, a very low amount of phosphate. So in the baby, the bones are tough and low mineralized, so they bounce. As you get older, they become stiffer. So maybe in old people, we need to understand this chemistry, find a drug that makes your bones tough. So when you fall over as an old person, it's like the baby, and it bounces and doesn't break. And that's the sort of direction we're pursuing. So now I want to change tack and quickly go on to bone structure. If we look at the femur, I've talked about the arrangement of these arcades. On this radiograph, you can see these thin slithers of bone are in very defined trajectories. That can be shown diagrammatically. And engineers, on a structure loaded in the same way, found the stress trajectories in tension and compression are also in those directions. And they made things called Fairbairn cranes. This is one on Bristol Dockside if you're ever in Bristol. So this is the same shape as a femur and is engineered in a similar way. Julius Wolff looked at bones on radiographs and came up with the idea that he thought these elements of bone were strategically placed, and the size of the bone related to the magnitude of load that was applied to it. And that was in about 1800s. So you could test that concept. You could say maybe there's an optimal amount the bone will deform. And if we increase it, we'll produce more bone, and if we decrease it, we'll produce less bone. This is Richard Hillam, a PhD student interested in bone strain on the human skeleton. And after a short negotiation and long period of getting ethical approval, we stuck strain gauges on parts of his skeleton to measure strains as he walked and talked. Interestingly, the highest strains in the skull occur when you're talking or laughing. So we then have a mechanism to measure deformation, and we can measure cross-sectional area or density. So we can look at functional adaptation. If you go to the gym, this is Paul in his youth, then you see your muscles get bigger. But actually, your bones will get bigger. Well, that's the general concept. And if you look at tennis players, their muscles and bones in their serving arm do get bigger. And if you look at triple jumpers, their bone mass compared with controls is significantly higher. So they're doing a lot of high strain loading, jumping. The tennis players doing unusual high velocity movements. And if you look at paraplegics compared with normal, you'll now see that the lower limb, the tibia, these two bones, is similar to the ones I showed you in osteoporosis, but the upper limb, which is predominantly now pushing the wheelchair, is actually as dense, if not denser, than the normal control. So this shows that your skeleton will adapt very specifically to the region where it's loaded or unloaded. You have to have a bit of fun in science. So one of the problems that we looked at also is if you go into long-term spaceflight, you lose bone. And you lose most of it from your lower limbs. And you can exercise in space, but the thing that's missing is the heel strike transient. When you walk, you put your heel to the ground, it will send a small jolt up your skeleton, which is attenuated as you go from your heel to your skull. In space, the most bone is lost from the heel and the least from the skull. So we thought this heel strike transient was actually important. This is walking over a force plate, and this is a sort of force impact of that heel strike transient. And we made a machine out of bits we found around the hospital, 2 cylinders with springs in. One cylinder, when the spring plunger went to the bottom, it released a weight which came up and hit the bottom of the foot. And that's just a technical drawing. We then had to show European Space Agency that astronauts could use it. So this is a nice compliant German astronaut, Thomas Reiter. We then had to convince them it would work in zero gravity, where we had to be the subjects. So this is myself and Geraint Williams, and this is an old Caravelle jet. And this was before Ryanair came on board. And this jet we had to fly in, and you'll see it goes up. It goes up slightly steeper than Ryanair jets. I started this one a bit late, but a bit early rather. So this jet goes up at about 50 degrees, and it goes over the top of a parabola, and then it comes down. Well, this was over Paris, actually, so if you were enjoying yourself in Paris, watch out, because we then start plummeting towards the ground, which is when we experience microgravity, and we had to show that all this equipment worked before they'd fly it up to the Mir space station. One Belgian colleague vomited 2 minutes after the first parabola and said, "Can we stop?" And they said, "Yes, in about 3 hours." So then we went and put it into the Euromir space station. We measured the astronaut before and after flight, the heel bone, on a DEXA scanner to look at the mineral content. And when he came back 6 months later, the red line shows the control heel, and the blue line's the impacted heel. So we've maintained bone mass. It's important to try and maintain bone mass. Once you've lost it, it's difficult to get it back. So on n equals 1, we showed we were right, and we just acknowledged the sponsors for that. Clint Rubin in turkey wings had been looking at the difference between no load, which causes porosis, small loads, which maintains bone mass, and increased loads, which produces more bone. And he showed that you could either do this with large strains a few times a day, or with small strains many times a day. And this led to some of the vibrating plates that you see around these days for stimulating bone. So in summary, the factors that affect bone are strains in your bone. Strains are deformations, and they result from gravity, but also from muscle, which is important in the elderly. And one of the important things is that bone strain and estrogen work synergistically. So if you take estrogen away, bone strain is not as effective. And that's one of the problems in postmenopausal osteoporosis. So in summary, cyclical loading, short periods a day are all you need, high strain rates, diverse types of exercise, and you can use these vibrating platforms. I just thought I'd put one in front of the kitchen sink for my wife, but she didn't agree. So let's just have a quick look at genetics. This is a bone. You may recognize it as a femur, and it has actually grown in a mouse that was not able to load its leg. It had a paralysis. This is one that was loading its leg, and it shows the refinements. So genetic templates are modified by mechanical refinements. This guy, Judex, in New York, did a CT scan of the distal part of the femur of 3 common laboratory mice, this part. And you can all see their different architecture. One is a wide, thin-walled tube, and one is a thick tube. So what? He then subjected these mice to reduced loading, and each of the strains lost different amounts of bone. This strain lost the most. He then increased the loading, and again the 3 strains were different, but not in the same ratios. So this tells us that it's not quite as simple as we thought. Hugh Montgomery at UCL showed that there was a particular gene that he was looking at, that if it was defective, if it had a polymorphism, it would change the strength, hand grip and vertical jump in females. And if you had this gene, and he tested this on a unique animal model called the Army Recruit, if you had this polymorphism, you could load your bone, but it wouldn't increase in mass. So we are all a bit different, and then we need to try and understand that, why people are non-responders. If you look at a whole range of laboratory mice in terms of bone as a material, then there's a 200% difference between mouse strains. And these 3 red circles are the strains I just showed you that had different responses to loading and unloading. Does it make sense? Well, it kind of does, because the weakest bone is the mouse that puts it in a thin tube farthest away from the neutral axis. So it's genetic compromise it's trying to adapt to. And the strongest bone, you can get away with a narrower, thick-walled tube. So there's a relationship between material properties and geometry. And even in racehorses, the Horse Race Betting Levy Board sponsored us to look at tendon and fractures in bones. And if we took ordinary horses and we looked at tendon strength and bone strength, within individuals, they were related. So if you had strong bones, you had strong tendons. And the common thing between tendon and bone, again, is the collagen, type 1 collagen. So we're quite interested in understanding this. The fracture is usually falling down, but you can fracture a bone, horses and humans, through normal loading. So maybe if you're not genetically predisposed to respond to loading and increase your bone, then you'll be like a paperclip. If we keep bending it and it doesn't repair, it will break. And these are microcracks that occur in the bone that eventually coalesce into those fractures. And these are two studies from different parts of the world that show as we get older, we accumulate more microcracks. But if you look at the old people carefully, some old people have no more microcracks than the 20-year-olds. We don't know their life histories yet, but we want to know why these do and these don't. And that has implications, and there are various theories that you can read on this slide as to why those different responses may occur in different individuals. And that's quite important in understanding population effects. So just to finish off with, how could we integrate that into understanding what happens in our bones? If we don't want to do lots of exercise, we can try and recover bone once it's been diagnosed as being lost in osteoporosis. And this study by Rubin and his colleagues, these women under 65 kilos, lightweight, thin women are the ones that tend to get osteoporosis. If you put them on a platform that doesn't vibrate, they lose this amount of bone. If you vibrate them, they don't lose that bone. Older, heavier women don't show that response. Can we do anything in young children? Well, these are adolescents. And again, if we vibrate them, they will put on some more bone. And the interesting thing is, in this slide, we're looking at the area of trunk muscle, and the vibration increases muscle. So bone will respond, and bone responds to various things. So in terms of our future research strategies, we need to know about genetic predisposition. There's no point in you exercising if your bones aren't going to respond. So we need specific programs for different populations. We need to look at lifelong exercises of muscle and bone. The Chinese are training their old ladies to do Tai Chi, which improves their balance, stops them falling down, stops them getting fractures. Muscle strength can be improved with lifelong exercise. A holistic approach to the whole neuromusculoskeletal interaction, not just drugs that will fix the bone cells. And then, as ever, evidence-based to make sure that these things are real. And if you go to some of these gyms, I don't believe the vibrating platforms are real. So today, of all days, the International Osteoporosis Foundation leaflet is something you should read. You should love your bones. The fast facts on nutrition and exercise are the building blocks. The more detailed stuff that links to what I've been telling you is that men and women are both at risk. Muscle is important. Vitamin D can strengthen muscle. If you exercise, you can get away with short bursts of high-rate loading, and you should condition your balance. And if you do revert to drugs, there are now drugs which will reduce the loss by stopping the cells that eat your bone away, or increasing the mass by stimulating the cells that produce it. And if you do that, then I found this lady on the internet who's 100 years old and is still shot putting. So there is muscle strength and vigor in us yet. So I think I ought to stop there, and thank you for your attention.
Well, thank you, Alan. So I'm sure that you have some questions for Professor Goodship. Lady here, there's a microphone there. Okay.
I'm interested in the disparity in attitudes between doctors in diagnosis. I just use me as a personal example. I was in Australia, and they do scanning over there automatically if you have an accident of any kind in a certain age group for women anyway. I had a scan, and it came back that I had early onset osteoporosis. When I came back and showed them to my local GP, she said according to the regulations or description here, she would not consider it. And so therefore what I was recommended to have when I was visiting Australia, she would not apply here. So I was put on vitamin D tablets. But I was just interested, she said the measurements of acceptability were different. I
think there are international differences, and I'm afraid in the UK we have a national disease service, not a national health service, in my opinion. And it's interesting, Australia would treat you and the UK wouldn't. there are rules and guidelines in the UK, and they usually come into play after someone has had a fracture in relation to the fracture and the age of the individual, and whether they go on to drugs like bisphosphonates automatically, or whether they have a DEXA scan, and according to their T and Z scores, they go on to drug regimes. So it's really down to healthcare policy. And I guess my view would be, as I've said, when you've lost bone, it's more difficult to get it back. So the earlier you start intervention, and there are interventions other than drugs you could use, I think sort of exercise is proven, and then get another scan to see if it's made any difference, because we're not very good at actually evidence-based follow-ups. No. So part of it is down to healthcare budgets and international guidelines, but the message I would give you is that the sooner you start to try and restore bone or stop the loss of bone, the better, and the less risk you'll have as you get even older.
Yes. There's a lady in the center.
I have osteoporosis, and I exercise by dancing, ballroom dancing, and play badminton and swim. I wondered if you could recommend, and I walk as well. I wondered if you could recommend particular exercises.
But the exercises that sort of fit in with the science would be ones that load your bone with a high rate, and these oscillations can be high. So your sort of badminton, squash, tennis would certainly do upper arms. Walking and swimming will condition other things like your cardiovascular system, your respiratory system, your muscle endurance, but not necessarily be most osteogenic for your bones. So for bones, short bursts, high strain rate, diverse loading patterns, and that's a component of the holistic exercise program. So I wouldn't stop your swimming and walking, because they do different things. It's not one cure fits all, I'm afraid.
And so you might suggest mixing some break dancing with the ballroom.
Yes. Ballroom might be a bit sedate.
I've got, there's one question at the back there, and then afterwards there's another question down here.
Do you know of a relationship between osteoporosis and osteoarthritis?
That's an interesting question, and it used to be said if you had one, you didn't get the other, but
yeah,
talking to my clinical colleagues, that's not really the case. And certainly we're looking at changes in arthritis, and again, there are changes in the mineralization of bone. And some of the thickening in bone in arthritis might be because the bone is actually getting softer as a material, so you need more of it as a structure. So there are various theories, and we're trying to use the Raman spectroscopy approach to tease out whether the chemistry of bone in arthritis that has thickened is normal or abnormal. And again, once you get a cue for, or a key to the mechanism, you can start developing therapeutic targets and drugs. But I think it is now not the sort of given that if you have osteoporosis, you won't get osteoarthritis and vice versa. It's more complicated, and that may be linked to genetics. And as we move forward, we unravel all sorts of things that complicate our simple interpretation of these things that we get initially.
So we can only take one last question, I'm afraid. So the lady here was...
Thank you. That was a fascinating lecture. I want to know, when you lose bone mass, do you actually lose mass? Are your bones actually lighter, or are they replaced with water which has got the same similar sort of density?
The bone material itself will be lost, as I showed you. In women, in the cancellous bone, the horizontal connections tend to go. In men, the whole network seems to thin down. The cortex will be thinned, and it does it from the inside, usually the internal part of the cortex, which in engineering terms makes sense because that is the least detrimental to the overall mechanics of the structure. And then that will fill up with marrow and other tissues. So it is actually an absolute loss of bone. Now there is a school of thought that says in osteoporosis it's not just a reduction in bone material, it's a change again in the collagen of the bone. Alan Bailey in Bristol published some work showing that in osteoporotic bone, the collagen can show a change. And that's why I'm particularly interested in this interaction between collagen and mineral.
Thank you.
I'm afraid we must close there because there is a class coming in. I'm sure that you can find Professor Goodship on the UCL website, and I'm sure that if you have other questions, he'll be happy to respond.
Probably.
Anyway.
It might be a while with my inbox as it is, but...
Right. So thank you again, Alan, and we'll welcome you next Tuesday.